In this episode, we look at out-of-band management, secure file transfer, and security service edge (SSE) as architecture ideas that support secure access and operational resilience. These topics may sound like separate tools, but they all answer a practical question. How do you safely reach, move, or protect something when normal access is risky, unavailable, or spread across many locations? Out-of-band management gives administrators a separate way to manage systems when the primary network is down, overloaded, misconfigured, or possibly compromised. Secure file transfer protects information as it moves between people, systems, partners, and services. SSE brings security controls closer to users, cloud applications, and internet access instead of forcing every decision through one traditional data center. The common theme is controlled access. You want the right people and systems to reach what they need, but through paths that are protected, monitored, and designed for failure. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. Out-of-band management means using a separate management path that does not depend entirely on the same production network used by ordinary users and applications. In-band management uses the normal network path. For example, an administrator may connect to a server or network device through the same network that carries business traffic. That can be convenient, but it creates a problem when the production network is unavailable or untrusted. If a router is misconfigured, a firewall rule blocks access, or malware disrupts normal communication, the administrator may lose the very path needed to fix the issue. Out-of-band management provides another way in. That path might use a dedicated management network, a separate console connection, a remote management interface, or a controlled service designed for emergency administration. The value is not only convenience. It gives defenders and operators a safer recovery path when normal access cannot be trusted. The key security idea with out-of-band management is separation. The management path should be separated from ordinary user traffic so a problem in the normal environment does not automatically remove administrative control. This can matter during outages, ransomware events, network misconfigurations, failed updates, or suspected compromise. If attackers gain access to the regular network, a separate management path may help administrators investigate, isolate systems, or restore service without relying on the compromised channel. But separation must be real and protected. If the out-of-band path uses the same credentials, same exposed network, same weak authentication, and same monitoring gaps as everything else, it may become another attack path rather than a rescue path. Out-of-band management is powerful because it can reach important systems. Anything that powerful needs strong identity controls, limited access, logging, and careful review of who can use it. You can picture out-of-band management during a network device failure. Suppose a firewall change accidentally blocks administrator access through the normal network. If every management option depends on that same path, the team may need to send someone physically to the equipment or wait longer to restore service. With a properly designed out-of-band path, an authorized administrator may reach the device through a separate management channel, review the change, and correct the problem. The same idea applies during a suspected attack. If the main network may be monitored or controlled by an attacker, a separate trusted path can help defenders work without exposing every action through the compromised environment. This does not mean out-of-band management should be casually available from anywhere. It should be reserved, protected, and tested. An emergency path that nobody tests may fail at the exact moment it is needed most. Out-of-band management also requires strong access governance because administrative paths are high-value targets. An attacker who compromises a management interface may be able to change configurations, restart systems, disable controls, view sensitive settings, or create persistent access. That is why management access should be limited to specific administrators and protected with multi-factor authentication, MFA, where appropriate. It should use separate administrative accounts rather than ordinary daily use accounts when possible. It should also be monitored closely because management activity is usually sensitive by nature. Logs should show who connected, when they connected, from where, what device or system they reached, and what changes were made. The management path should not be exposed broadly to the internet or to ordinary internal networks. You want out-of-band management to be available to the right people during trouble, not discoverable and usable by anyone who finds it. Secure file transfer is another architecture concern because organizations constantly move information. Files may move between employees, departments, partners, vendors, cloud services, backup systems, customers, and regulators. The files may contain contracts, reports, logs, software updates, medical information, financial data, intellectual property, or security evidence. Sending files carelessly can expose sensitive data even when the systems storing the data are well protected. Secure transfer focuses on protecting confidentiality, integrity, and sometimes authenticity while the file moves. Confidentiality means unauthorized people should not be able to read the file. Integrity means the file should not be changed without detection. Authenticity means the recipient should have confidence about where the file came from. A secure architecture should define approved transfer methods instead of leaving people to choose whatever is easiest in the moment. Different transfer methods provide different levels of protection and control. Secure File Transfer Protocol (SFTP) uses Secure Shell (SSH) to protect file transfer sessions. Hypertext Transfer Protocol Secure (HTTPS) uses Transport Layer Security (TLS) to protect web-based transfers. Managed file transfer platforms may add scheduling, automation, access control, logging, approval workflows, encryption, and delivery confirmation. Encrypted email or secure portals may be used for some business exchanges. Older or weaker methods, such as Basic File Transfer Protocol (FTP), can be risky because they may not protect credentials and data properly in transit. The important Security Plus idea is not that one method solves every case. The important idea is that file transfer should be intentional. The chosen method should match the sensitivity of the data, the identity of the sender and recipient, and the organization's logging and retention needs. Secure file transfer is not only about encryption in transit. You also need to think about access before and after the transfer. Who is allowed to upload the file? Who is allowed to download it? Does the link expire? Can the recipient forward it? Is the file scanned for malware? Is sensitive data detected before leaving the organization? Is the transfer logged? Is the file encrypted at rest while waiting to be picked up? What happens if the wrong person receives access? These questions matter because a file can be protected during movement and still be mishandled at the destination. For example, a secure portal may protect the transfer, but if the recipient account is shared by several people, accountability is weak. A transfer link may use encryption, but if it never expires, it may become a long-term exposure. Secure transfer includes the whole life cycle around movement. File integrity is a useful concept when files are transferred between systems. If an organization sends a software package, configuration file, evidence file, or report, the recipient may need confidence that the file arrived unchanged. Hashing can help verify that the received file matches the original. A hash is not the file itself. It is a fixed-length value generated from the file's contents. If the file changes, the hash should change too. Digital signatures can also help prove that a file came from a trusted source and was not altered after signing. These ideas matter because attackers may try to tamper with files in transit, replace legitimate downloads with malicious ones, or modify evidence. Even when encryption protects the communication path, integrity checks provide another layer of confidence. Secure architecture often uses multiple protections because no single control should carry the entire burden alone. Security Service Edge is a modern architecture concept for delivering security controls from the cloud, closer to users, devices, and applications. SSE is often discussed in environments where users are remote, applications are in software as a service, SaaS, platforms, and data no longer sits only inside one corporate data center. In older designs, remote users might connect through a virtual private network, VPN, back to the company network, and then reach the internet or cloud applications through centralized security tools. That can create delay, complexity, and bottlenecks. SSE changes the model by placing security functions in a cloud-delivered edge service. Instead of sending every path through one physical location, The organization can apply security controls wherever the user and application traffic actually are. The goal is secure access without depending entirely on the old perimeter. SSE commonly includes several kinds of security functions. A secure web gateway, SWG, helps protect users as they access websites and internet services by enforcing web access policies and blocking risky destinations. A cloud access security broker, CASB, helps apply security controls to cloud applications, such as visibility, policy enforcement, and protection for sensitive data. Zero Trust Network Access, ZTNA, helps connect users to specific applications rather than giving broad network access. Data Loss Prevention, DLP, may help detect and control sensitive information leaving approved boundaries. These functions may be delivered as part of one service or integrated through a broader architecture. You do not need to memorize product packaging. Focus on the purpose. SSE brings access control, threat protection, data protection, and visibility closer to modern cloud and remote work patterns. SSE is closely related to secure access because it changes the question from how do you get onto the network to how do you securely reach the specific resource. A user working from home may need a cloud document platform, an internal application, and safe internet access. A traditional model might send that user into a corporate network first, even if the application is already in the cloud. An SSE model can evaluate identity, device posture, application, data sensitivity, and risk before allowing access through a cloud-delivered control point. This supports the zero trust idea that access should be specific and contextual. The user may be allowed to reach one approved application, but not the whole internal network. If the device is unhealthy or the location is risky, the service may require stronger authentication, restrict download, block access, or alert security staff. The security value of SSE depends on correct integration with identity, devices, data policies, and logging. If identity information is inaccurate, access decisions may be wrong. If device posture signals are missing, the service may trust unsafe endpoints. If cloud applications are not connected to the policy layer, sensitive activity may go unseen. If logs are not collected and reviewed, the organization may not understand who accessed what or which policies were triggered. SSE can simplify some architecture problems, but it does not remove the need for planning. It also creates provider dependence because security decisions may rely on a cloud-delivered service. That means availability, performance, contract terms, data handling, support, and outage planning matter. A cloud security control is still a critical service, and critical services need governance, resilience planning, and clear operational ownership. These three ideas connect through the larger theme of controlled paths. Out-of-band management creates a controlled path for administration when the normal path is broken or untrusted. Secure file transfer creates a controlled path for moving data between people, systems, and organizations. SSE creates controlled paths for users reaching cloud, web, and private applications through cloud-delivered security services. In each case, the path should be deliberate, protected, monitored, and limited to its purpose. A hidden management interface, an unapproved file-sharing shortcut, or an unmanaged cloud access path can become a serious weakness. Architecture should make safe paths easier to use than unsafe ones. People should know how to manage systems during emergencies, how to transfer sensitive files properly, and how access to cloud services is evaluated. Strong design reduces the need for improvisation during stressful moments. Out-of-band management, secure file transfer, and security service edge all show that architecture is about more than where servers sit. It is about how access works when networks fail, when data moves, and when users and applications are no longer gathered behind one simple perimeter. Out-of-band management helps administrators keep control when ordinary access is unavailable or risky, but it must be strongly protected because it can reach powerful systems. Secure file transfer protects data in motion, but it also requires attention to identity, authorization, integrity, logging, and what happens after delivery. SSE brings cloud-delivered security controls to modern access patterns, but it must be integrated carefully with identity, devices, policies, and monitoring. The main lesson is that secure access needs design pathways. When the pathway is clear, limited, and visible, the organization can work, recover, and protect data with much more confidence.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.